In this video, we're going to study a new type of function called a logarithmic function. Now, the context that this arises in is in the context of exponentials. All right, so let's suppose for a second that I have a function g of x equals 4 to the x. Okay. Now, first of all, over here on the left, we're going to remind ourselves of what g of x looks like. It's the function with exponential function with a base of 4, so we know that it goes through the point 0, 1 and the point 1, 4. Okay, those are two special points, and it has a horizontal asymptote at y equals 0. And so there's what our function looks like. But what I want to do is be able to solve g of x equals 3. I want to be able to solve this equation. Now, first of all, let's notice that if you look at the function g, it is a one-to-one function. Remember, it passes the horizontal line test. That makes it a one-to-one function. Now, if a function passes the horizontal line test, remember that that means that it has an inverse. So that means there is a function out there that is the inverse of g. In other words, it undoes whatever g does. So if I was to take that function, whatever it happens to be, and I take the inverse of both sides of this equation, then I know that's going to solve that equation for me. I know that on the left side, the inverse undoes the function g and just gives me x back again. And then whatever that inverse function evaluated at 3 is going to be my answer. Now over here, I can see that not only does this inverse exist because the original function passes the horizontal line test, but I also know some things about it. First of all, because the point 0, 1 is on the original function, what we learned about x and y switching when it comes to inverse functions tells me that 1, 0 is on this inverse. It also tells me that 4, 1 is on this inverse because 1, 4 is on the original. So we know that it looks like that. We also noted there's a horizontal asymptote here at y equals 0 for the original. And so because we're symmetric about the line y equals x, we also know that we have a vertical asymptote for the inverse. All right, so here's our inverse function. And we give this inverse function a name that is specific to the base of the exponential that it's the inverse for. So here's what we say. It's the logarithm base 4 of x. Okay, so we put the base of the exponent that it goes with just down here as a small kind of subscript number, and we call this the logarithm, which we'll abbreviate log. So on the next page here, here's kind of our formal write-up of what's going on. It says that the logarithm base b of the function, written as log base b of x, is the inverse of the exponential function b to the x. Now, there are two particular logarithms that happen often enough that we give them special names. So if the base is e, then we say it's the natural logarithm of x, okay, as opposed to log base e of x. And when the base is 10, a lot of times we won't bother to write the 10, we'll just write log of x. So if you see either of these, just know that they mean log base e or log base 10 respectively. Now, there's a few properties of logarithms we should be aware of. First of all, the log base b of 1 is equal to 0. And remember that the reason that is because if 0, 1 is on y equals b to the x, then the flip of that, 1, 0, would have to be on the inverse, right? Is on y equals log base b of x. So in other words, if I put a 1 in for x, I should get a 0 for y. That's where property number 1 comes from. I also know that if 1b is on y equals b to the x, right, then b comma 1 is on y equals log base b of x. So if I put a b in for x, then the y should be 1. Okay, that's what property number 2 says. And then properties 3 and 4 are just that inverse function property, right? If I compose an inverse with the original function, I should get x back again. And if I do the composition in the other direction, I should also get x back again. All right, but down here is probably the most useful formula for us. It tells us how to convert from logarithmic form, a logarithmic form equation to an exponential equation. So notice the base of the logarithm, we call this the base of the logarithm, becomes the base of the exponent. What you're taking the logarithm of is what your exponent is equal to, and what the log is equal to becomes the exponent. Now I think the best way to just really remember this is that the log base b of c, what is it? At its essence, it is the number you raise b to in order to make c. Okay? So this number is what we raise b to in order to produce this number inside here. Okay, so it'll take a little while to get really comfortable with this interchange, but this is really the most important one to really have down really well. All right, so let's do some examples where we put this thing into practice. So first of all, I'm just going to write it again up here, right, where what I'm saying is the log base b of c equals a, right? A is the thing I raise b to in order to make c. So when I say the log base 3 of 9, and really there's parentheses here, even if I don't write them, or taking the log base 3 of 9, we're saying that's equal to x, right? So there's two ways to think of it. If I go back to that previous page and I just kind of read this, the log base b of c is the number we raise b to in order to make c. Okay, so I could kind of recite that to myself. The log base 3 of 9 is the number I raise 3 to in order to make 9. Well, because we know that if raising 3 to the second power makes 9, that means 2 is our answer. Okay? The other way of doing this is to more directly just use this formula here. So to literally say the base of my logarithm becomes the base of the exponent. What my logarithm is equal to becomes the exponent. And then the number inside is what the exponential part is set equal to. And then if I look at it this way, then it's also clear that, oh, if I put x equals 2 in here, I will make 9. So x equals 2, and so regardless of how we approach it, the answer is 2. So we say the log base 3 of 9 equals 2 because raising 3 to the second power makes 9. So here's another one. The log base 1/2 of 1/8. Okay. Now you might in your head just realize, oh, if I take 1/2 and I raise it to the third power, that gives me 1/8. And so if that's you, you can just right off the bat say the answer is 3. Okay? But it's understandable if that doesn't come to you right away. And if that's the case, just set it equal to x and say to yourself, all right, the base becomes the base of my exponent. What the logarithm is equal to becomes my exponent, and that's going to be equal to 1/8. All right, so here I can say 1 to the x over 2 to the x, just basically distributing my exponent through, is equal to 1 over 8. But 1 raised to anything, really doesn't matter what it is going to just be 1. So this is 1 over 2 to the x is equal to 1 over 8. But again, we know that if I raise 2 to the third power, I get 8. So we get that x must be equal to 3. All right, so let's look at another one here. So again, if you can figure this out just by looking at it, fantastic, but don't feel the need to. So we're going to do the log base 10 of 1/10. So I'm trying to figure out what that is, so I can give it a variable name, x. So we're saying 10 to the x is equal to 1/10. Now, in the last two questions, we were able to look at these pretty easily and just see 3 to the second power is 9, 2 to the third power is 8. In this one, it's 10 to the x power equals 1/10. So if the answer's not immediately jumping out at you, what you want to do is make the bases on each side match one another. So, for example, I can make 1/10 into a 10 if I call it 10 to the negative 1, right? Then I can have this base and this base match one another. And the moment that the bases match one another, then I can see exactly what x should be. So x would have to be negative 1 in order to make this equation work. So there's my answer. So the log base 10 of 1/10 is negative 1, and it makes sense because 10 raised to the negative 1 power is 1 over 10. All right, here's an expression involving an exponential raised to a logarithm. So here's one of those special names that we've given to our logarithmic functions here. We see the natural log of 4. So first of all, we'll see that this is e to the natural log of 4, but that really means it's e to the log base e of 4. So remember, I'm getting that just from what the natural log means. But then let's also remember that if you have e raised to the log base e of 4, that just equals 4. And we're getting that from our property that says, it was property number 4, which says b to the log base b of x is always just going to equal x. Why? Because the exponential b to a power and the log base b are inverses of one another, so they're just going to undo. So the e and the natural log kind of undo and just give us 4 back. We really have the same thing, same sort of thing happening here, okay, where we say this, we know log without a little 10 there really just means log base 10 of 10 to the third. But I know automatically that that's equal to 3. How do I know that? Because property number 3 said the log base b of b to the x is equal to x. All right, so the exponent is what kind of survives after the log and the exponential zap each other. All right, so let's take a look at example 7. So in example 7, again, we know that if there's no base here, it really just means the log base 10 of 0.0001. All right, this one might be a little bit less obvious, so I would say it might not be a bad idea to go ahead and just set it equal to x and then rewrite it in exponential form, right? So again, remember what's happening here is that if you have the log base b of c is equal to a, then that means b to the a equals c. So this means 10 to the x equals 0.0001. And so what I would suggest is that we approach this problem kind of like we approached example 4 from before, where I'm going to try to make this side have a base that matches the exponential side. So I would like to write this as 10 to a power. So the first thing I'll do is write this thing as a fraction. So 0.0001 we know is really 1 over 10,000. Right? It's 1/10,000th. Now, if I've got 1 over 10,000, I would really prefer it if this was a 10 instead of a 10,000. But I can do that, right? Because a 1 followed by 4 zeros we know is really just 10 to the 4th power, right? And that'll produce 10,000. And then finally, in order to get the tens on the same level, we just bring that 10 to the 4th up and make the exponent negative. And so once I do that, then it's easy to see, okay, my x should be -4. So the log of 0.0001 is equal to -4. So two more examples here. First of all, example 8, we have the log base 2 of the square root of 2, right? So log base 2 of the square root of 2 equals x. So that would have to mean that 2 to the x is equal to the square root of 2. All right, now as we've done, we would like to write both sides with the same base. And if I can do that, then I can just look at the exponents to see what the answer is. Well, we have to just remember here that a square root is the same as raising to the 1/2 power, right? So this might be just a little bit of quick review here, but remember that if you have the nth root of x to the m, then that gives you x to the m over n power. Sorry, a little error there. So that is x to the m over n. And if you have just the nth root of x to the 1st power, then that is just x to the 1 over n. And so remember, if there's no particular root specified, what it really means is the square root. So this means that 2 to the x is equal to 2 to the 1/2. So that means that x itself must be a half. And so what is this really saying? It's saying raise 2 to the 1/2 power if you want the square root of 2, which is exactly what this property says. All right, lastly, this one's a little trickier. All right, it's asking for the log base 27 of 1/9, right, is equal to what? So understand first, the base of the logarithm becomes the base of the exponent. What the logarithm's equal to becomes the exponent, and that's equal to 1/9. Now our goal should be to write both sides written as the same base. Okay, so if you look at 27 and 9, let's think about what base might they have in common, right? Or in other words, 27 and 9 should be something raised to a power. After thinking about it a bit here, we should recognize that 3, right, could be raised to a power to give 9 and to give 27. So we can look at 27 first of all and notice that 27 is the same as 3 to the 3rd power. However, we understand that we're going to take 27 and raise it to the x, so it's going to be 3 to the 3rd power raised to the x. So I literally just replaced 27 with 3 to the 3rd. And then 1 over 9, well, 9 is 3 squared. All right, but before I can really tell very well what x is, I know that I need to get both the 3's in the numerator. So on the left side, to simplify this, we have a power raised to a power. So we recall our exponent rule that says x to the m raised to the nth power is x to the m times n. So we multiply the exponents when we raise a power to a power. So this is 3 to the 3x. And then on the right side, I can make this 3 be up in the numerator if I just change the exponent to -2. So 3 to the 3x equals 3 to the -2. That must mean that 3x equals -2. So I'm literally just setting these exponents equal to each other once the bases are the same. And if I just divide both sides by 3, I'll have my answer. So this is telling me, right, the log base 27 of 1/9 is -2/3. Or in other words, if you raise 27 to the -2/3 power, you will get 1/9. Okay? And you can actually easily check that in a calculator. Type in 27 raised to the -2/3 and it will spit out to you the answer of 1/9.